Alright, well, welcome to the solution to test 2 video, I suppose. I don't always do these, but since there was interest, I'll go ahead and do it. And here we go. So problem 1, I give you a particular force law, f of x is equal to minus k times x plus beta x squared. So this is kind of like a modified spring, right? A spring with a little extra term here. And then the question is to find a potential energy function for F. So what you want to do is you want to find a function whose derivative gives you back the force if you multiply by minus, right? So we need that minus for the definition of potential energy. And so basically we just got to integrate this formula here with respect to x. And so when you do that, well, first of all, there's a minus here and a minus there, so they cancel. You're just faced with du dx is equal to, the constant k plus beta x squared. So we integrate, and when we do that, we get a constant, which could be anything, and then the k is a constant, so it factors out like that. And I just integrate the x, 1/2 x squared, integrate beta x squared, gets me 1/3 beta x cubed. All right. So you could have put u not equal to 0 here, or you could have could be any constant, right? You have that freedom to set the potential energy to be 0 wherever you like in this sort of problem. Let's see here, then what? Omit units and suppose just for this part that k and beta are both 1, find the work done by the force from going from x equal to 0 to x equal to 1. So there you would calculate the second here, let me get the camera to work. There you calculate the work integral, right? Integrate the force over the distance. And in that case, of course, that's equal to minus du dx, but then by the net change theorem from calculus, we get minus u of 1 minus a minus u of 0. And when I plug those up in here, the u naughts cancel, of course, and you're just left with minus 1/2 minus 1/3, and the 0 gives you nothing. All right, so that gives you minus 5/6, which is about minus 0.833. So, I don't think this problem is particularly difficult, and I think you guys could get it if I was to ask it, or something like it again, right? Let's see here. Most people got the next problem right. So here we go. You're given a graph of a potential energy for a particular particle under the influence of a conservative force, so that means the energy is conserved, right? I tell you the total energy of the particle is 3 joules, and so the idea here is just to think about where's the 3 joules. So here's the 3, and you look across here, and only in this region and in that region are you going to have that the total energy is larger than the potential energy. So these are the regions in which you'd have positive, or I should say non-negative kinetic energy, which is the only thing that's physically, classically reasonable. So that gives us approximate answers of about 16 to 25 and 33 to 46 meters. And I didn't quibble if you just put the 16 and 25 and 33 and 46 here. I didn't fuss about it. I don't know. I grow weary of taking points away from some things like that as we go on here. All right. So problem 3, pretty standard momentum problem. We had some problems like this in the homework, I believe. I think we've had problems pretty much like everything on this test in the homework one way or another, if you really go back and look at it. But let's see here. So suppose 2 carts slide along an essentially frictionless track. Cart A has mass 20 kilograms, B has mass 60 kilograms. A travels rightward with initial speed of 13 meters per second. The carts collide. A moves to the left at 6 meters per second. Cart B moves to the right at speed 15 meters per second. All right. Find the initial speed and direction of cart B before the collision. Also, was the collision elastic? Now, I announced in the test, right, that you had to think there was some kind of like explosion in the collision, because it turns out that as we calculate this, the kinetic energy is more after the collision than before. If you like, a way to get rid of the explosion is you could just time reverse the problem. I could give you the before is the after is before, then then you wouldn't need an explosion. You could just chalk up the loss of energy to the collision process, right? So that's just a comment. All right, so anyway, this is one-dimensional, so we can do the momentum before equal to the momentum afterwards. I use plus for right, I use minus for left. So I've got plus 13 meters per second here, I've got minus 6 meters per second there. Not taking account of these signs would make the problem, would make your answer wrong. We don't know VB naught, we'd like to figure it out, so we solve for that by algebra, and that gives you this, which works out to 8.667 meters per second approximately. All right. Now, so I asked the question, was it elastic, right? So you need to answer that. A few people forgot to, and sorry about that if you're such a person. That's easy enough to fix next test, right? Although I'm not trying to think, are there, well, I guess there could be some rotational collisions in the next test, that's true. Okay, so anyway, certainly on the final this is a possible problem, right? Because the final is comprehensive. Okay, so I worked pretty hard to prove a theorem for you guys that the relative velocity before and after a one-dimensional elastic collision was negative in comparison to its before and after. So the relative velocity here would be 4.33 meters per second before, and it's minus 21 meters per second afterwards. Obviously these are not negations of each other, right? So it's not elastic by the theorem that we had. Or you could straight calculate the kinetic energy before, about 3,944 joules, versus afterwards, 7,110 joules. As you can see, this is not an elastic collision because kinetic energy is not conserved. I had you guys tell me all kinds of crazy different stuff about why it was or wasn't elastic, but it was a sticky collision. It wasn't a sticky. The collisions being sticky is that almost, it pretty much guarantees it's not elastic, but it doesn't prove that it's elastic. The definition of elastic is kinetic energy is conserved. So you could have a bouncy collision where kinetic energy was not conserved. It's not enough for it to not stick. It has to be that the kinetic energy is conserved. If that's the definition of elastic collision. All right, so you need to clarify that if you don't know. Let's see here, next one. Problem 4 here. Yeah. So we got a 4-gram bullet fired horizontally into a 2-kilogram wooden block resting on a horizontal surface. Coefficient kinetic friction between the block and the surface is 0.3. Bullet remains embedded in the block, which is observed to slide 0.5 meters along the surface before stopping. What was the initial speed of the bullet? This problem is a play on the ballistic pendulum problem. All right, this is a variation of the ballistic pendulum problem. Same concepts involved here, just no strings. So the way we solve such a problem is we have to conserve momentum. All right, so in the process of the bullet getting embedded in the mass, we conserve momentum. So mv naught is equal to m naught plus m1. Here m naught's the mass of the bullet, m1's the mass of the block. And this gives me that the initial velocity of the bullet is actually the ratio of m naught plus m1 over m naught times the initial velocity of the bullet block system. Now the bullet block system slides 0.5 meters, and in so doing it loses kinetic energy to friction. So we have the kinetic energy initially, 1/2 m naught plus m1 times v1 squared is equal to the work done by friction, which is the force of friction times the distance here. Now the force of friction is the coefficient of static friction, or excuse me, kinetic friction times the mass times GD, because the normal force is directly perpendicular here to the surface. No funny business, no angles, anything like that going on here. And so you can solve this, and you get v1 is the square root of 2 mu GD, which then I can go back to my other equation and get v naught is the ratio m naught over m1 m naught times the square root of 2 mu GD. And then if I plug in the constants that I get 859.04 meters per second. A lot of you guys gave me 39.8 meters per second, something like that. That comes from ignoring, that's basically what you're giving me is the initial speed of the block. But we didn't ask for that here. I asked for the initial speed of the bullet, which is different and much faster. So anyway, some of you are about halfway correct there. That's why I gave you half credit. So let's see here. Problem 5. Hey, listen, I feel your pain. I did the same thing on my test once upon a time, like I told you guys about. But, you know, let's see here. Well, if you didn't get anything wrong on the test, it wouldn't be a productive experience, right? If you get something wrong on the test, you've got something to learn, right? If you had a perfect score, then, I mean, the test was kind of a waste of your time, right? I just, none of us feel that way, really, truth be told. Okay, so you have a 1,000-kilogram car traveling 40 meters per second, 2,000-kilogram truck, as you can see, I have a very realistic picture here, traveling 25 meters per second that way, 40 meters per second that way. They stick together after the crash, all right? And I said find the velocity, magnitude, and standard angle of the car and truck immediately after the crash. So if you try to do this problem without vectors, you're probably just wrong. Okay, I mean, like, it's hard for me to salvage much from your solution if you didn't use vectors here. So conserve momentum, mass of the car, velocity of the car, mass of the truck, velocity of the truck is equal to the final velocity of the mass of the car-truck system. And so if I solve for VF, I get, you know, this one over the total mass times the initial momentum. Plugging in the numbers, like so, I get that. And then you work it out. I get 13.33 meters per second and 16.67 meters per second for the final velocity, which is actually the initial velocity of the, you know, the car and truck after they crash together and as they start skidding, you know. So here's a picture of that. You've got, it's in quadrant 1, right? So the standard angle is relatively easy to figure out here because you can just use inverse tangent of the y over the x, which gives me a 51.35 degrees, and the magnitude is the length of the vector, which is the square root of the sums of the squares of the components, as we should know. And of course it's the speed, so the units are meters per second. All right. Problem 6, I said hypothetically, all right, suppose that you had the initial speed of 10 meters per second, there's a coefficient of kinetic friction 0.4. How far would it take for the car and truck to skid to a stop? So much like the bullet problem, so sorry, this problem's kind of a rerun, right? It's kind of the same as the other problem, but oh well. 1/2 mv naught squared equals to the work done by friction. In this case, of course, that's mu m gd. So I can solve for d. I've got v naught squared over 2 mu g, which ends up giving me 12.76 meters. I was watching out if you had used the correct speed from problem 5. If you used, instead of using 10, use 21.34, you would get 58.09 meters, which is like, that's a really long, it's a pretty long way to slide, isn't it? So I mean, in practical terms, it would have definitely hit a guardrail or whatever, you know, in practice. There's not many roads that are 58 meters across like that. But anyway, problem 7. Problem 7, we have an inclined plane and a horizontal plane pictured below. No friction. The spring and the board have a very small mass compared to the 2-kilogram mass pictured at the top of the incline. Give the length is let me look at here. This length is 14.3 meters. The angle beta is 40 degrees. It takes a force of 20 newtons to compress the spring a distance of 1 centimeter from its equilibrium. The mass m slides down the incline across the plane, compresses the spring a distance of 1.2 meters just before bouncing back. What's the initial speed which was given to the block? All right. So this is, you know, pretty clearly a conservation of energy problem. We had a bunch of these in the homework, and so I thought it was a reasonable question, but this has stumped quite a few of you. Let it not be so on the final, if I asked a similar question. Anyway, so first of all, to figure out the spring constant K, we can use that 20 newtons is the force of the spring, which is Kx, right? That's 1 centimeter, and that gives me a spring constant of 2,000 newtons per meter. All right, great. Then I need to come to terms with how high that box is versus the L. And so since tangent beta is opposite over adjacent relative to the angle, that's L over H, which gives me that H is equal to L over tangent beta, I think. Yeah. So, goodness gracious, if I found an error today, that would be very annoying. Maybe not for you guys, but for me. Anyway, so conservation of mechanical energy says that the initial potential energy of the box plus the initial kinetic energy of the box, which we don't know, all right, is equal to 1/2 kxf squared, because after it slides down here and compresses, all of the energy is in that potential energy of the spring, all right? So the formula for potential energy of the spring is 1/2 kx squared. If you didn't know that, you could integrate the force and figure out the potential energy, right? We did work that out. Anyway, so if I solve for V naught squared, I get this, kxf squared minus 2mgh divided by m. There's your V naught. Take the square root of both sides. Take the square root, gives me V naught is this guy right here. And when you plug in the numbers into that, it looks like this. And then crunch it, and you get 33.26 meters per second. You notice that the units make sense here. You got a Newton over meter times meter squared divided by kilograms. So like the kilograms, they be canceling. And this gives you a meter squared. That gives you a, well, this gives you a meter squared. This gives you a second squared after the kilograms cancel. So you got meters squared over second squared. Likewise over here, you got a meter squared over second squared. When you take the square root, you get back to meters per second. You know, it's not a bad idea to check the units on your formulas as you're doing things, just to make sure you're not deceiving yourself and, you know, making up some unphysical nonsense formula. Although you guys don't do that too much. Let's see here. So, problem 8 is a center of mass problem. So it's, you know, relatively straightforward. I give you the position of mass 1, mass 2, and I let the position of mass 3 be variable. I even suggested variables for you, A, B, C. I told you the center of mass is at 3, 3, 2. And so you don't actually need to know the mass to figure this out, because when you work out the math, the masses, they end up canceling, right? Because you get the m here and here and here and here, so they cancel. And they just end up giving you the ABC is twice the center of mass, minus 1/3 the position of 1, minus 2/3 the position of 2, and then when you plug in what you got, well, you get 1, 2, 3. So there you go. The third mass was apparently at 1, 2, 3 in centimeters. All right. Not much to say there about problem 8. It's kind of cut and dried. All right, so problem 9. Let's see here. I said find the work done by the force F equals to this. All right, e to the ax, b sine ky, 2cz, along the path from the origin to x1, y1, z1, and I give you that the constants are all non-zero. Now, so I warned you guys, if you're ever asked a question about find the work from one point to another and they don't tell you the path, that's a dead giveaway. It has to be a conservative force, right? Because you can't calculate the work done along a path you're not given, unless the only way that question's reasonable, right, is if the work done along any path is the same. So, and it's much easier to use the potential energy theorem as opposed to actually do the work integral along any path you might think of, right? And so some of you were doing something like taking the dot product of the force with this position vector. That just doesn't even make sense, because this force is variable. You can't take a variable force and dot product with the displacement. That will not give you the work. It's just nonsense. The only time you can take a dot product of the force with the displacement is if the force is constant. This force is not constant. It is varying with x, with y, with z. All right. So you have to go through the calculus here. All right. It's not that complicated. You just have to find the potential energy function. And so that amounts to here doing an antiderivative with respect to x, with respect to y, with respect to z. And as you do that, it suggests minus 1 over a e to the ax, b over k cosine ky, and minus cz squared. And you can, there's no common term here, so you just take one of each of these, put them together, and you can easily check that if this is my potential energy function, if I was to calculate the gradient of this, right, as we defined, well, the gradient's up here actually, minus the gradient, right, partial u, partial y, partial z of the potential energy function, you put minuses out front according to our definition of potential energy, and you can get back this e to the ax b sine ky and 2cz from this formula, right? So it checks, right? It's easy to check. Just take the derivatives with respect to x, y, and z respectively. Make sure that they give you back what you're supposed to, like that. All right, everybody can do this. If you do calculus 1, you can do this. Not a big deal. And then so the curve goes from where it goes from the origin to x1, y1, z1. So by the theorem that we derived in class, you get the potential energy of minus the potential energy of the final point plus the potential energy of the original point, and that works out to this right here. So u0, 0, 0 gives me a minus 1 over a and a b over k, and that's 0. So I get these terms here from the 0, from the origin term, and then the other ones are from the x1, y1, z1, obviously. So there you go, that's the work done. So there's that. Again, I don't think that problem was that difficult, really. I think all of you could do that if I was to ask something similar on the final, right? Now, the last problem on any of my tests is almost always something more challenging, and so that's what this was. Some of you got some sense of what this problem was about, but no one answered it completely. All right, so let's talk about this one. So if you have this force, 1 over x squared plus y squared minus yx, I asked you to directly calculate the work done, and this little circle here just means that it's a closed loop. That's just a notation to say, hey, it's a loop. All right, so the loop I'm looking at here is the circle of radius r, given the, oopsie, look at that. Missing my curly bracket here, aren't I? Oh well, don't tell anybody. Anyway, so given the counterclockwise orientation for the circle, all right, so basically we're just talking about this guy, all right, counterclockwise, so like this. All right, so here you go. All right, so just the circle of radius r, right, like that. What's the work done by this force as you go around the circle? And so I said, first of all, calculate it directly, and then next, try to find a potential energy function for F, all right? Then I asked a question, is it a conservative force? Discuss. Explain the seeming contradiction. So what's the deal? So this is a circle. I think I put on the board for you guys that x was equal to r cosine theta and r is equal to sine, well, r cosine t, y is equal to r sine t, is a parameterization of that circle. Something that I have never talked about in class, but I would talk about in more detail when I teach Calculus 3. There are many details of Calculus 3 I'm leaving out. Like I have told you guys, the bare bones of Calculus 3. Just what you need for physics, no more. You know, there's much more to say. For instance, like how do I know that the work is done if I parameterize it this way and not another way? Well, there's a theorem that doesn't matter how you parameterize the circle, the work done along the circle, as long as we're just talking about going around the circle once, right? If you, okay, fine, if you wind around it twice, then it's different, but supposing that you have, you know, reasonably comparable parameterizations of the circle, they just go around once in, say, you know, smooth fashion, you can prove that the work done is independent of your choice of parameterization. So the work done is really just a consequence of the curve and the force involved, and it doesn't even care about the time dependence of the path as it happens. Kind of interesting, actually, physically speaking. But anyway, the point here is that if you plug the parameterization into F and work it out, you just get the this x squared plus y squared, of course, is equal to r squared on the circle. So that appears. So you get r squared downstairs, but that r cancels with the r that appears in the minus y and the x here, which just leaves you with 1 over r minus sine t cosine t, all right? And so, on the other hand, the velocity for the parameterization is minus r sine t, r cosine t. So you notice that the velocity and the force, they're they're parallel. They're in the same direction, right? So when you take the dot product of them, you just get the square of their magnitude. So again, this is the definition of work: is you integrate the power. The power here happens to be equal to well, the power is 1. This works out to 1. So you integrate 1 from 0 to 2 pi, you get 2 pi. So the work is 2 pi. Now, I gave you guys a theorem about conservative vector fields. We learned, I mentioned at least, that they're path independent, right? So if you calculate the work done from one path, from one point to another, same beginning and ending points, you get the same work done from going from start to end, right? You have path independence. I said also you have the integral around any loop is 0, all right? Also you have the existence of a potential energy function, right? So this is a loop, and the work done around the loop is non-zero, so it seems like you shouldn't be able to find a potential energy function. But you can try nonetheless, right? You can try, and so I did. And I think a couple of you got this. Potential energy function, give or take a sign or something, but if you do the integration, like basically just partial integrate with respect to x, if you tilt your head and squint, you can see that this is the partial derivative of inverse tangent of y over x. And this is the partial derivative of y of inverse tangent of y over x. So there's a different chain rule involved here, but this is just basically, I'm really just doing inverse tangent integral here with a substitution, right? So granted, this is harder than the integral I did in the previous problem, but this is the bonus problem, right? So anyway, and yeah, so apparently the potential energy should be minus the inverse tangent of y over x. That gives you minus the gradient of u equals to f, which is like, then you're like, wait a minute. I thought you just said that the force wasn't conservative, but now you're showing that it's equal to minus the gradient of the potential energy function. That's a contradiction, because your definition of conservative force was it equals to minus the gradient of potential energy function. Okay, so this is not so fast, all right? Here's the thing. There's a fine print. There's a fine print involved, because you have to have f is equal to minus the gradient of the potential energy function over the whole domain of the function. And so that's the thing. C is a loop, all right? And we have that non-zero integral. But if f was conservative on D, a subset of R2, then the integral around the loop should be 0, right? For all loops inside D. So that means f is not conservative, yet it seems we found a potential energy function, right? But here's the thing. The potential energy is only defined for x not equal to 0. And in fact, f is conservative, not on the whole plane. Notice that the very definition of f does what? It's singular, right? It's not defined at the origin. And it's exactly this place where the force blows up. That's in some sense where this non-trivial integral is coming from. See, because the theorem about loops being 0, it's only true if the loop can be smoothly deformed to a point in the domain. So the fact that there's a hole in the domain, that's why this is possible, all right? And the careful statement of this requires us to understand something called simply connected. And so anyway, the math we're bumping up against here is the origins of what's called topology, and wrestling with these issues is what ultimately led to many of the main advancements of mathematics in the 20th century, give or take, I would argue. And it's all there in just plain old, vector physics. But anyway, so that's it. That's the contradiction, is that the issue is that it's conservative, but it's not conservative on a region which contains the origin. The force is only conservative as long as you're looking at a region without holes, which doesn't contain the origin. If you contain the origin, then it's not conservative because you've got this non-trivial integral. And vice versa, this formula that we found, it actually doesn't work all the way around. It has to have an angle jump. If you look at it, right? This formula, it doesn't work if x is equal to 0. And this is the inverse tangent that you know, but you could talk about other branches of inverse tangent, like that were defined. You could talk about other inverse tangents which were not defined on like some other thing other than x equal to 0. Essentially, this is coming because your inverse tangent gets you angles in quadrants 1 and 4. You could have a different idea of inverse tangent which gets you angles in like quadrants 1 and 2, all right? But somewhere there's going to be this angle defect. Anyway, this is a mystery I can only fully explain in Calculus 3, but anyway, there it is. So I guess that's it for this one. Thanks, guys.